Usually when we talk about a medical diagnosis or um, like recognizing a face in a crowd, there's this expectation of instinct.
Mm.
You look at a messy scrawl on a whiteboard and your brain just instantly says, oh, that's the letter B.
Yeah, exactly. The human cognitive architecture makes that classification feel, well, entirely effortless.
Yeah.
We don't perceive the underlying computation. We just arrive at the result.
Right. But the moment you try to program a computer to do that exact same thing, you realize just how much heavy lifting our brains are actually doing in the background. The magic vanishes, and you're left staring at a mathematical Wild West.
Oh, absolutely. It is a completely different world under the hood.
So today, we're doing a deep dive into a comprehensive Wikipedia article covering the origins, the underlying mathematics, and the real-world applications of pattern recognition. We are going to look at how algorithms actually learn to see and understand the chaos of the physical world and, translate that into a framework you can use to understand the technology surrounding you every day. Okay, let's unpack this.
Sounds great. I mean, the foundational architecture for machine pattern recognition didn't actually start in computer science at all. It started in psychology.
Wait, really?
Psychology.
Yeah, because to build a machine that can recognize the physical world, early researchers had to formally define how human perception works in the first place. You can't replicate what you don't understand.
That makes sense. And before we get into the heavy algorithms, we need to establish a critical baseline difference that the text points out. People use the terms pattern matching and pattern recognition interchangeably all the time.
Oh, constantly.
Hmm.
But mathematically, they operate on completely different logic.
Right, because pattern matching is rigid. It's like the salto plus F function on your word processor. You type in a specific word, and the system looks for that exact byte sequence.
Yeah, if there's an extra space or a slightly different character, the match fails entirely. It's binary. It's either a perfect match or it's nothing, which makes pattern matching virtually useless for processing the natural world. Pattern recognition, fundamentally, is the science of accounting for statistical variation.
Exactly. The real world is noisy.
It's the messy handwriting problem.
Huh.
Every time your friend writes the letter A, the physical geometry is slightly different, like the angle shifts, the ink bleeds, maybe the loop is open, but your brain still recognizes the underlying concept of the A.
Right, and the psychological literature in our source material breaks down this human ability to handle variation into two main hypotheses. The first one is called template matching.
Okay, how does that work?
Well, this posits that your brain basically holds a vast library of stored templates in long-term memory. When a new visual stimulus hits your retina, your brain rapidly cross-references it against the library until it finds a geometric fit.
But the source text points out a pretty massive flaw in template matching, which is scaling.
Yeah, the math just doesn't work out.
Right, because if you have to store a unique template for every conceivable variation, size, and rotation of the letter A, your brain, or, a computer's memory, would run out of storage almost instantly.
Exactly. It's highly inefficient. Which brings us to the second hypothesis, and this is the one that really built modern computer vision.
Feature detection.
Yes. What's fascinating here is how early computer models were directly mapped from this specific cognitive theory. The text highlights Oliver Selfridge's pandemonium system from way back in 1959.
1959, wow, that's early.
I know, right? Selfridge proposed that we don't look at whole templates. Instead, we break a stimulus down into subcomponents. We observe a capital letter E not as a single solid image, but as a hierarchical collection of features.
Like 3 horizontal lines, 1 vertical line, and 4 right angles.
Exactly.
So the cognitive process is essentially an assembly line. The lowest level of the brain just looks for edges. The next level looks for corners made of those edges. The next level looks for shapes made of those corners. We're mechanically tallying up geometry without ever realizing we're doing it.
That's beautifully put. And that hierarchy of abstraction is literally the blueprint for artificial neural networks today.
But, knowing that an E is made of lines doesn't help a machine unless we have a mechanism to teach it what a line actually is in the first place.
Right, because a machine doesn't wake up understanding the concept of a horizontal line. It just sees a grid of raw pixel values, numbers.
Which brings us to the training data. The algorithm has to be taught, and the source outlines 3 dominant learning procedures. First, you have supervised learning.
Ah, yes, the brute force educational approach.
Yeah, you feed the system a massive data set that humans have already painstakingly hand-labeled. So you feed it 1 million images labeled cat and 1 million images labeled not a cat. and you mathematically grade its homework until its internal parameters align with human consensus.
It's effective, but incredibly labor-intensive. Then you have unsupervised learning, where the training data has absolutely no labels at all.
Just raw data.
Just raw data. The algorithm is dropped into a data set and instructed to find inherent structures or hidden geometries without any human guidance whatsoever.
Mathematically, this usually takes the form of clustering, right?
Yeah, exactly. Calculating the distance between data points in a multidimensional space to group things that share statistical similarities, even if the algorithm has no idea what those things actually are.
And finally, there's semi-supervised learning.
Right, which is sort of a hybrid. It uses a tiny sliver of labeled data to anchor the system, and then a massive ocean of unlabeled data to flesh out the boundaries of the patterns.
Hold on, I want to challenge a specific claim the text makes about this because it really caught my eye.
Oh, what's that?
The source states that KDD knowledge discovery in databases and corporate data mining have a much stronger focus on unsupervised methods.
Yes, they do.
But that seems incredibly counterintuitive to me. If you are a massive bank or a retail giant, just letting an algorithm wander through an unlabeled data lake looking for random correlations sounds reckless.
I can see why you'd say that.
I mean, how do you trust an insight or base $1 million business decision on it if you never gave the algorithm a defined target to look for? Aren't businesses risking massive, expensive hallucinations?
Well, the risk is real, sure, but the economics make it entirely unavoidable. In the modern corporate ecosystem, data collection is completely automated and virtually free. Every click, every transaction, every dwell time metric is recorded.
Right. We generate mountains of data every second.
Exactly. But hand labeling that data requires human domain experts, which is prohibitively expensive and time-consuming. Unsupervised learning mathematically surfaces latent variables that humans wouldn't even think to look for.
Okay, give me an example.
Well, a retailer doesn't need the algorithm to know what a sneakerhead is. They just need the algorithm to cluster the data points and reveal that a specific demographic grouping consistently buys, like high-top shoes, premium headphones, and energy drinks at 2 in the morning.
Oh, I see.
Unsupervised methods don't hallucinate the correlation. They calculate the geometric proximity of those behaviors in the data space. The human executives then step in afterwards to assign the business meaning to that cluster.
So the algorithm organizes the chaos into discrete piles, and the humans decide which pile is gold and which pile is garbage.
That's a great way to put it.
But let's look at how the machine actually digests this information. Because whether it's supervised or unsupervised, the machine isn't looking at a picture of a sneaker or a customer profile. It is processing an instance of data, which is described by a feature vector.
Right, and a feature vector is really just a mathematical coordinate.
So if you're analyzing a medical patient, the vector might include their age, their exact blood pressure, a categorical value like their biological sex, and maybe an ordinal value assessing their pain on a scale from 1 to 10.
Yeah, and each of these features represents a different dimension. So a patient with 50 recorded medical metrics is represented as a single point floating in a 50-dimensional space.
Which is wild to think about, but the text points out a massive mathematical bottleneck here, often called the curse of dimensionality.
Oh, it's a huge problem in machine learning.
Because if your instance has thousands of features, say, analyzing every single pixel in a high-resolution image, the computational load becomes impossible. The algorithm basically drowns in the noise.
It does. It can't figure out what's important.
So the source contrasts two specific techniques to solve this: feature selection and feature extraction. And the distinction between the two dictates how transparent the AI will ultimately be.
Yeah, the mechanism behind each approach is fundamentally opposed.
So I was thinking about this, and I came up with an analogy. Think of your raw data as a massive pile of ingredients for a salad. You have lettuce, tomatoes, croutons, bacon, carrots, and maybe 50 other things.
Okay, I'm following you. A 50-ingredient salad.
Right, so feature selection is an algorithm looking at the bowl and deciding to just pick the most statistically relevant items. It keeps the lettuce and tomatoes and actively throws the croutons and carrots in the trash because they're redundant. The data set shrinks, but the features that remain are still entirely human-readable. You still have a tomato.
I love that. You've reduced the dimensions by simply discarding the less informative axis of your data space. The tomato is still an identifiable axis.
Exactly. But feature extraction is a totally different beast. The text mentions principal component analysis, or PCA.
Yes, PCA is a classic.
Feature extraction is like taking all of those salad ingredients, the lettuce, the tomatoes, the croutons, and throwing them into an industrial blender. You grind them down into a completely new, mathematically dense smoothie.
Okay, the smoothie.
Exactly. The dimensions are reduced, the redundant information is compressed, and the math runs lightning fast. But you can no longer point to the smoothie and identify the tomato. The original human meaning is gone.
The underlying math of PCA really explains why that smoothie is so powerful, though. PCA looks at that 50-dimensional cloud of data and calculates the specific direction or axis where the data varies the most.
So it finds the widest spread of the data?
Right. It then mathematically rotates the entire space so that this line of maximum variance becomes the new primary axis. It compresses the data by finding the fundamental structural components, even if those components don't map to anything humans have a word for.
We get a smaller, denser coordinate.
Yeah. Once the data is transformed into this optimized low-dimensional space, the algorithm finally has to make a decision, and this requires probabilistic classifiers.
Right, because rather than just shouting a definitive answer, the most robust pattern recognition systems output a mathematically grounded confidence interval. They output the n-best list of possible labels alongside their probability percentages.
This is a crucial feature for real-world applications.
So an email filter doesn't just categorize a message as spam. It calculates that the vector sits in a region of the data space that is like 85% likely to be spam, 10% likely to be a newsletter, and maybe 5% likely to be a genuine message from your accountant.
And the critical architectural advantage of this probabilistic output is the mechanism of abstention.
Abstention, meaning it can choose not to answer.
Exactly. If the highest probability on that n-best list only hits 30%, the algorithm is programmed to abstain. It throws an error code or flags the instance for human review.
Because in a multi-stage machine learning pipeline, where the output of one pattern recognizer becomes the input for the next, forcing an algorithm to guess on ambiguous data is catastrophic.
It creates a domino effect.
Right. The text calls it error propagation. The first algorithm makes a bad guess on a blurry letter. The second algorithm uses that bad letter to hallucinate a wrong word. And the third algorithm uses that wrong word to completely misinterpret a critical financial document. The system corrupts itself.
Abstaining acts as a firewall against cascading failure. But, the concept of algorithmic confidence requires us to examine the foundational mathematical philosophy of how these systems define reality in the first place. We really have to look at the formal problem statement of pattern recognition.
The text defines this as approximating an unknown ground truth.
Yes, the algorithm never assumes it possesses absolute knowledge. It attempts to approximate the true nature of the data by navigating what's called a loss function.
A loss function. Okay, let's break that down.
Imagine a mathematical topographical map representing the penalty for making a mistake. The algorithm is essentially rolling a ball down this multidimensional landscape, trying to find the absolute lowest point, the minimum error rate.
So it wants to find the bottom of the valley.
Exactly. But how you set up the math to find that valley depends on which statistical tradition you follow, the frequentist approach or the Bayesian approach.
The frequentist approach feels like the more intuitive, objective path, at least to me.
It does, yeah. It treats the parameters of the model, like the mean or the variance of the data clusters, as unknown but fixed objective values. The algorithm uses techniques like Fisher's linear discriminant.
Which sounds intimidating, but what does it actually do?
Well, imagine a 3D cloud of data points representing two different categories. Fisher's linear discriminant calculates the exact 1D line through that space that allows you to project the points onto it so that the two categories are pushed as far apart as possible while keeping the points within each category tightly packed.
Okay, I can picture that.
The frequentist relies exclusively on what the collected data proves. It's strictly empirical.
But the Bayesian approach is where the text completely blew my mind because it directly connects modern computer science to ancient philosophy.
Oh, the Kant connection.
Yes. The article explicitly references Immanuel Kant's philosophical distinction between empirical knowledge, things we learn by observing the world, and a priori knowledge, which are the fundamental truths we know before we ever make an observation.
It's wild to see it applied to coding.
We are talking about epistemology, the actual study of how we know what we know, literally functioning as the engine for modern machine classification.
If we connect this to the bigger picture, Bayesian statistics formalizes the process of updating your beliefs based on new evidence. In a Bayesian classifier, the developers can manually inject a priori knowledge into the system.
Like giving it a head start.
Exactly. For instance, if you are building an algorithm to recognize rare diseases, You know a priori that disease X only occurs in 1 out of 1 million people. You program that prior probability into the math from day one.
Okay.
As the algorithm takes in empirical observations, the patient's feature vector, it calculates the likelihood of that specific data occurring. It then multiplies the prior knowledge by the new likelihood to generate a posterior probability.
It mathematically balances subjective expert context against raw, objective data. So what does this all mean? We've traveled from the cognitive psychology of the 1950s to data smoothies, through the multidimensional landscapes of loss functions, all the way to Kant and the philosophy of knowledge. Why does this matter to you, the listener, navigating the world today?
Yeah.
What are the practical stakes of these mathematical valleys and feature vectors?
Well, the evolution of pattern recognition maps directly to the evolution of modern risk. The text details how early adoption was often hindered not by technological limits, but by institutional inertia.
Yeah, there is a brilliant, highly specific historical footnote in the source about optical character recognition, or OCR.
Oh, the banking story.
Yes. By 1990, the pattern recognition required to read handwriting had advanced to dynamic capture. A digital stylus wouldn't just capture the static image of a signature, it captured the time series data.
Which is so much more secure.
Right. It recorded the speed, the specific acceleration curves, and the physical pressure of the pen strokes. It was an incredibly robust feature vector that could definitively confirm identity and eliminate bank fraud.
And yet the banking industry largely rejected the implementation.
Because capturing that time series data required the banks to change their physical checkout counters and slightly inconvenience their customers with a new stylus device.
It's unbelievable.
The banks ran a cost-benefit analysis and realized it was easier and cheaper to just let the fraud happen and collect the insurance money from the FDIC than to deploy the pattern recognition technology.
The math was completely ready, but the human economic incentives were misaligned. But contrast that 1990s banking environment with the modern high-stakes applications detailed in the article.
The stakes are a bit higher now than forged checks.
Oh, drastically. Today, we rely on computer-aided diagnosis, or CAD. Systems like Papinet, which the text highlights for cervical cancer screening, process cellular feature vectors to detect anomalies human pathologists might miss.
Life-for-death situations.
Exactly. We are deploying these algorithms in defense targeting systems and in autonomous vehicles where the machine has literal milliseconds to calculate the loss function between identifying a shadow, a blowing plastic bag, or a pedestrian stepping into the road.
Yeah, you can't just bill the FDIC if the self-driving car gets the vector space wrong.
Yeah, you cannot. This raises an important question. As we embed these systems into the critical infrastructure of human life, how comfortable should we be relying on algorithms that fundamentally do not know anything?
Because they're just calculating shapes.
Right, an autonomous vehicle doesn't understand the tragedy of hitting a pedestrian. It is merely executing a Bayesian update or minimizing a loss function based on extracted pixel geometries. It is an approximation of truth operating at lightning speed.
Which perfectly frames the journey we've taken today. We started by dismantling the illusion of effortless recognition, looking at how Oliver Selfridge's pandemonium system mapped human perception onto machine architecture.
Back to the subcomponents.
Right. And then we explored the massive, multidimensional training grounds, where algorithms sort through unlabeled data lakes to find hidden clusters of human behavior.
Yeah.
We broke down the mechanics of feature extraction, blending raw data into compressed mathematical smoothies to avoid the curse of dimensionality.
Say goodbye to the tomato.
Say goodbye to the tomato. And we examined how the ancient philosophical debates about a priori knowledge now power the Bayesian calculations driving our medical diagnoses and our transportation. You are now equipped with a conceptual framework to look at the smart technology around you and understand the mathematical Wild West operating beneath the glass.
The magic is really replaced by a profound appreciation for the statistical architecture defining our modern reality.
But there is one final concept from the source material to leave you with. In the See Also section of the text, there's a link to the concept of a black box.
Ah, the black box problem.
Yeah. A black box is a system where you can observe the inputs going in, and you can observe the decisions coming out. But the internal mechanisms, the specific mathematical paths taken to reach that decision, are completely opaque.
We can't see the work.
Exactly. As feature extraction becomes more aggressive, blending our medical data, our financial histories, and our behavioral metrics into high-dimensional vectors that human brains cannot visually or conceptually interpret, The system's logic disappears into the math.
It becomes unreadable to us.
If an algorithm accurately recognizes a pattern of disease in your health data, or a pattern of risk in your behavior, but the black box is so deeply abstracted that the machine cannot explain how it arrived at that truth, what do you do with that answer?
That's a chilling thought.
When the mathematical smoothie can't be unblended, do you blindly trust an unexplainable equation that has mathematically calculated a deeper pattern in your life than you can see yourself? Something to ponder the next time your phone seamlessly anticipates your next move. Thank you for taking this deep dive with us. Keep questioning the patterns around you, and we'll see you next time.